Okay, so now let's talk about how we define line integrals of analytic one forms for merely continuous functions in a way that's consistent with the way we did it for piecewise C1 curves. So we have gamma, just a continuous curve, and f, an analytic function on U. And so step one is just like what we did with 1 over z. We'll break up the interval AB into tiny pieces so that gamma on these small intervals sits inside a disk where there exists an antiderivative of f, and I'll call it capital Fj defined on dj. So that's step one, and we'll talk about how you do that in a moment. And step two then is that you can define the integral of f over this continuous curve as follows. So this is what you would get if you had a piecewise C1 curve. You would break it up into these onto these subintervals, and you'd compute the differences of the values of these antiderivatives at all of these endpoints. But here we also have a problem. We don't know if this is well defined. We already did mention that this expression here doesn't depend on the choice of antiderivative on this interval, again, because antiderivatives are unique up to a constant, so if you change it by a constant here and here, it gets subtracted out. But it did depend on the manner in which we broke up our interval. So how do we address the construction in step one? Well, here's our secret weapon, which is the Lebesgue number lemma, which just says let X be a compact set in a metric space with a finite open cover. So X is a subset of a union of finitely many open sets. Then there exists a positive number delta such that for any set A inside our compact set X, that should be, with diameter less than delta, so that would mean that for any 2 points in A, the distance between them is less than delta. So for sets with small enough diameter, you can fit them in completely inside one of the sets in the open cover. So there exists a J such that A is contained in Vj. So using the Lebesgue number lemma, we can address step one. And this is important to see at least once because this is an argument that you see a lot in algebraic topology. So step one, what was it? Let's put it over here. Step one was to break up our interval into pieces where we had antiderivatives. So we'll do it by first finding antiderivatives on a bunch of disks. So for every t in this interval, well, we can certainly find a disk containing gamma of t on which f has an antiderivative, because on any disk centered at this point contained in our domain, f will have an antiderivative using power series. Okay, but by continuity, the inverse images of these disks will be relatively open subsets of the interval AB. So we'll get an open cover of the compact interval AB, but it's compact, so we have a finite subcover. So interval AB is contained in finitely many of these sets. Okay, and then now here is where we use the Lebesgue number lemma. And I'll use it with an n instead of a delta. So delta would be thought of as 1 over n. And basically, these intervals will have diameter, well, I'm breaking up the interval AB into an even, into n pieces. So for n big enough, these sets will have diameter small enough so that each one will sit inside of one of these sets V, that when I map it back into the complex plane with the path, it sits inside a particular disk. So it would sit inside of dTj. And so this gives a way of sort of evenly subdividing AB so that gamma restricted to these pieces will sit inside one of these disks on which we have an antiderivative. So the Lebesgue number lemma is a technical tool that makes lots of hand-wavy arguments rigorous in this subject. Okay, in step 2, why is our definition well defined? Again, here was how we defined it just to kind of match with what happens for piecewise C1 curves. So you break up the path into pieces on which we have antiderivatives and then just use the formula that we had for piecewise C1 curves. Well, we already said that this difference is independent of choice of antiderivatives, but then if you had a different way of covering it, you could pass to a refinement and then show independence of the covering, because you could show that on the refinement you were just looking at differences of antiderivatives on coverings of the refinement, and there's a little bit to argue there, but basically it's a matter of passing to a refinement and showing you get the same thing on the refinement. Okay, and this is consistent with the piecewise C1 case, because it's created directly from a formula we had in the piecewise C1 case. One nice thing you also see out of this is that when you break up gamma into all of these pieces on which you have antiderivatives all the way along, you can replace gamma with gamma tilde, which is a piecewise linear curve, just kind of connecting the endpoints. And you end up doing the same computation right here. And so you get that f integrated over gamma would be the same as f integrated over gamma tilde, because I just need to match all the endpoints when I move in close enough. Okay, so this is how we define these line integrals for f analytic, but gamma merely continuous. You break up gamma into pieces on which f has antiderivatives, and then you compute those differences of antiderivatives.